Hi everybody, welcome to topic number 23, radicals and radical functions. In this video, we're going to find square roots, cube roots, and n roots. We're going to approximate roots, and we're going to simplify radicals using the exponent rules of the product rule and the quotient rule. So a radical expression is made up of a radical sign and a radicand. The radicand is just what's inside of the radical sign. The most common radical sign that you all are used to is the one that's written here, which is the square root. Couple rules about square roots. If I take the square root of any number, it is called the principal or non-negative square root of that number. And if I take the negative on the outside of that square root, it's just simply called the negative square root. We remember that square roots and squareds are the opposite of each other. 3 squared is simply 3 times 3, which is 9. Well, the square root of 9 is 3 because 9 can be broken down to 3 times 3. A square root is just a number that can be multiplied by itself. Now, one of the things we have to remember about square roots is that because this number has to be positive, when we do a number times itself, there's no way to be able to get a negative number if the numbers are going to be the same. So this number on the inside always has to be positive. Now we can go through and simplify a lot of these square roots like we've done before. The square root of 36 is 6 because 6 times 6 is 36. Even with a decimal, treat it the same way. The square root of 25 is 5. The square root of 4 over 49, we could think of it as just the square root of 4 over the square root of 49. The square root of 4 is 2, and the square root of 49 is 7. The square root of 9, x to the 12th. Well, again, that's the square root of 9 and the square root of x to the 12th. The square root of 9 is 3. And when I take the square root of x to the 12th, I'm literally just dividing the exponent 12 by 2, and I'm getting x to the 6. So the square root of 9x to the 12th is simply 3x to the 6. Here I'm doing the opposite of the square root of 81. Well, the square root of 81 is 9, but it wants the opposite here. So that when you see on the negative on the outside, it's asking for the opposite. However, here, this wants the square root of negative 81. This is asking for a number times itself to be negative 81. But there's no way that you can take a number that's negative and multiply it by another number that's negative and get a negative on the inside. This will end up having no solutions. We cannot take the square root of a negative number. If you try to take a square root of a negative number in a calculator, it generally will come back and say undefined or error. We can extend our knowledge of finding square roots to find other roots, such as cube roots. So in a square root, when we go through and we take the square root of a number, we're looking for a number that multiplies by itself. For a cube root, we're doing the same thing, except it has to multiply by itself 3 times. Multiply by itself 3 times. So when I read the cube root of 8, I'm asking what number times itself 3 times gives me 8. And they get 2 because 2 times 2 times 2 equals 8. I use 3 2's to get there. So the cube root is a number that multiplies by itself 3 times to get the inside. Taking a look at the cube root of 1, what number times itself 3 times gives me 1? Well, that's simply 1 because 1 times 1 times 1 equals 1. The cube root of negative 64. So forgetting the negative for a second, what number times itself 3 times will give us 64? And we know that that answer is 4. 4 times 4 is 16 times 4 is 64. But can we do a cube root with the negative on the inside? Well, if it holds true, then all of these should have to be negative 4. What happens when I multiply negative 4 by itself 3 times? Negative 4 times negative 4 is positive 16, but I multiply it again by a negative 4, and I get a negative 64, which is what I have here. So the cube root of negative 64 is negative 4. So unlike square roots, we can actually take the cube root of negative numbers, because when I multiply a number with negative, and if I do it 3 times, it will come back to be negative. So cube roots can be both positive and negative numbers. Here, when I have it with variables, we're going to look at it two ways. We're going to look at it, what's the cube root of negative 27? What number times itself 3 times will give me negative 27? I know it has to be negative. What number times itself 3 times will give me 27? Is 3. 3 times 3 is 9, times another 3 is 27. Then I'm going to look at the cube root of x to the 15th. Now when I did square roots, all I did was take the variable and the exponent and I divided it by 2. But now all we're going to do is divide it by 3. So I'm going to take the inside 15 and I'm going to divide it by 3 and I'm going to get 5. So the cube root of negative 27x to the 15th is negative 3x to the 5th. Since we can raise real numbers to powers other than 2 and 3, it makes sense that we could take cube roots, or we could take roots of real numbers other than square and cube roots. We call these nth roots. So an nth root is really just us going through and finding any value for our root. The n is called the index. In a square root, we never really see it. So, for example, in a cube root, this is the index. We call it the index of 3. If I put a 4 here, here is the index again. This is simply known as a fourth root, whereas this one here was a cube root. For a square root, we leave the index blank. So typically for a square root, we leave this blank. This would be a square root. Okay, so the index is telling you what root we have it for. One of the more important things is this last line here. It is understood that that the 2 is there for 2 for an even index, the radicand must be non-negative to take the root. For an odd index, the number can be negative or positive. So what that means, if you remember, with a square root, you can't have a negative on the inside. For a cube root, you could. So if your index is even, your number on the inside must be even. So for the fourth root, the number on the inside must be a positive number. If I go through and take a fifth root, this number can be odd. So the inside of the radical can be odd as long as the index is odd itself. If it's even, then the number on the inside must be positive. Let's take a look at some more examples. We've done these before, but let's do them again. The square root of 16 over 81 is just the square root of 16 over the square root of 81, which is 4 over 9. Here, we're okay to take the square root because the negative is on the outside. This is asking for the opposite of the square root of 49. Well, the square root of 49 is 7, and the opposite of 7 is negative 7. Here I'm going to take the square root of 16 and the square root of b to the 4th. The square root of 16 is 4, and the square root of b to the 4 is just taking the 4 and dividing it by 2. So leaving me with b squared. The cube root of negative 1 is negative 1, because negative 1 times itself 3 times gives me negative 1. Again, if it's a negative on the inside, that's okay as long as the index is odd. The cube root of this fraction, we'll break it up and we'll do each number separately. What number times itself 3 times gives me 8? That's a 2. And what number times itself 3 times gives me 125? That's a 5. Same thing here, we will break this up. We will do the number, and we will do the exponent. What number times itself 3 times gives me negative 8? It's okay to be negative because this is odd. So this will be negative 2. And then for this here, we'll take the exponent and divide it by the index. 3 divided by 3 is 1. Here's some higher roots. So to the 4th power, we're asking what number times itself 4 times gives me 16. Well, if you think about 16, 16 is just 4 times 4. And each of these 4s become 2 times 2. So I have 4 2's here. So the 4th root of 16 is 2. I want the opposite of the 4th root of 81. So I need to figure out what number times itself 4 times give me 81. Well, 81 is 9 times 9. And each of the 9 times 9 gives me 3 times 3. So I have 4 sets of 3. So the fourth root of 81 would be 3, but the negative means I want the opposite of it. So it means the answer has to be negative 3. This one says, what number times itself 4 times gives me negative 81? Well, think about it. If I had all these 3's and I turned them into negative 3's, what would happen? These two negative 3's would become 9, and these two negative 3's would become 9, and 9 times 9 is 81, but it doesn't give me negative 81. There's no way to get a negative number with multiplying the same number by itself 4 times, which makes sense. The index here is even. That means this can't be negative. That means there is no solution for this problem. Here for 32, we're looking what number times itself 5 times gives me 32. It's okay that it's negative because this is odd. Well, 32 is just 16 and 2, and 16 is 4 and 4, and each of these 4's become 2's. So here I've got 5 sets of 2's. We'll make sure it's negative, so we have negative 2 here. For the x to the 20th, we're just going to divide it by 5 because our index is 5. We always just take the exponent divided by the index. 20 divided by 5 gives me 4. So this would simplify to negative 2 x to the 4th. 4 to the x, the fourth root of x to the 16th, again, we could just take the power and divide it by the index. This would give me x to the 4th. And here we're going to just kind of do each part separately. We have the fourth root of 256, the fourth root of x to the 12th, and the fourth root of y to the 8th. Well, 256, we can kind of go through, and we can see that's 2 and 128, which this would be 2 and 64, and this would be 2 and 32, and this would be 2 and 16, and this would be 4 times 4, and this would be 2 times 2, and this would be 2 times 2. So if you look here, we actually have 8 2's, which really means that this could have ended up being a little bit easier, right? If we go back and look at this, 256, it means this could have been 16 times 16, and each of these 16's can be 4 times 4 and 4 times 4. So here's my group of 4. The fourth root of 256 is 4. For this, we're going to take 12 and divide it by 4. That gives me 3. And for the y, we'll take 8 divided by 4, and this gives me 2. We will take a look at this, what we call prime factorization, later on in the class in a couple of topics. Now in these examples, you'll notice that we're taking a radical, already something that's raised to a power. So again, a reminder, radicals and powers cancel each other out. So when I take a look at this, I have a square root of negative 3 squared. The square root and the squared will actually cancel each other out, and it will just leave me with the inside. And that should happen every time. The square root and the squared cancel, leaves me with the inside. Here this is a fourth root taken to the fourth power, so they will cancel, and it just leaves me with x minus 2. As long as the index matches the power, it will cancel out and simply leave you with the inside. Now this here, we'll break it apart. The square root of 25 will become 5, and here the square root and the squared cancel and just leaves me with the inside of x. Now this guy, x squared plus 2x plus 1, we can actually factor. What's a number that multiplies the 1 that adds the 2? They would both be 1's. So this is x plus 1, x plus 1, but since this is the same, we can rewrite this as x plus 1 squared. Again, the square root and the squared cancel out, and all it leaves me with is x plus 1. So again, radicals and exponents cancel each other out as long as the index and the radical are the same. So if I have a square root, I need to use a squared to be able to cancel it out. And it works either way. The squared is on the inside and the radical is on the outside. They will always go through and cancel out. When we evaluate radicals that do not produce rational numbers, we may use the product and quotient rules to help us simplify. So again, this goes back to exponents. In exponent world, if you have two bases that are the same, you could just multiply them together and add their powers. And that's the same here with the index. As long as the indexes are the same, we can multiply the numbers that are on the inside. Same thing when we divide. As long as the index is the same, we can go through and split them up. Let's show you what we mean on these problems. So here, both of these are square roots. If I want to make sure I just multiply them, I take the two numbers and I multiply them inside. 5 times 2, this gives me square root of 10. Same thing here. Because both of these are in the cube root, we'll just go through and multiply 7 times 9. This gives me cube root of 63. These are both square roots, so they both can go under the same square root. So I'll have 5x times 3y. 5 times 3 is 15. X times y stays x times y. And again, these are both fourth roots, so I could put everything under there. The 5 and the 4 will go through and make 20. So again, as long as they have the same index, you can basically combine them into one square root. If I need to simplify with division, we just make sure that the radical goes to both the top and the bottom as we've seen before. So this would be square root of 9 over square root of 64. This we can simplify. Square root of 9 is 3. Square root of 64 is 8. Here, we'll make sure both the top and the bottom get the fourth root. And then we'll look at each part separately. Now the top, this is just 1x. There's nothing we're really going to be able to do with that, so we'll leave that as the fourth root of x. But here at the bottom, this is the fourth root of 16 and the fourth root of y to the fourth. The fourth root of 16 is 2, because 2 times 2 times 2 times 2 gives me 16. And the fourth root of y to the 4 is simply 4 divided by 4, or y. So this bottom part simplifies to 2y. So we would leave this as our top answer. Again, we can't really simplify the fourth root of x because there's only one x here. We'll do the same here with the cube root. It'll be the cube root of 2 over the cube root of 8x to the 9th. Well, there's no number times itself 3 times. It's going to give me 2. So the cube root of 2 can stay. But what number times itself 3 times gives me 8? Well, that is 2. So we'll take that out of the radical. And here we could do 9 divided by 3, and we get 3. So here the radical disappears completely, and we leave this as our answer. It is okay to leave a radical on the top. We'll learn later on we don't want to leave radicals on the bottom if we can. We'll do the same with this. This is just the square root of x to the 12th over the square root of 25y to the 8th. The square root of x to the 12th is x to the 6th. The square root of 25y to the 8th is the square root of 25, and the square root of y to the 8th. The square root of 25 is 5, and the square root of y to the 8th is y to the 4th. Remember, with square roots, we just take half of the exponent. So half of 8 was 4, and half of 12 was 6. For the last one, we'll leave this negative till the end because all it's telling me is I'm going to take the opposite of whatever we're doing here. So we'll do the cube root of 125x over the cube root of y to the 9th, and we'll leave the negative here. Now at the top, we have the cube root of 125 and the cube root of x. What number times itself 3 times gives me 125? Well, that's 5. And I don't have enough here to get rid of the cube root on x. We'll leave this 5 cube root of x. Cube root of y to the 9th. We'll take 9 divided by 3. This leaves me with y to the 3. But again, remember we have this negative on the outside, which goes along with it. So the negative stays on the outside here. And this is my final answer. So as we simplify with radicals, we make sure each the top and the bottom part get the radical, and then we try to simplify it as far as it can go.